We all have heard how great quantum computers are, but did you actually know that they are really bad at talking with each other? The reason is it's very difficult to transfer the information from the quantum computer to the internet. It's challenging to build a quantum network. In the next few minutes, I'm going to show you how we use tiny little drums, like this one, to transfer the information between the quantum system or quantum computer and the internet. Hi, my name is Irene, and I am an experimental physicist here at the Technical University of Munich. In the past few years, we all have seen a huge progress in the development of quantum computers, especially the one from Google and IBM. However, what you perhaps don't really know is that it's currently very difficult to build a quantum internet. So we don't have a way to make quantum computers that are very far apart to communicate with each other. But let's take a step back. How do our classical computers do this? So if we have two normal computers very far apart, the information between them is traveling through the internet, something we use every day. But how does actually the information travel? It does it through optical fibers, through light. So this is an optical fiber that I have here. So an optical fiber is basically a cable, as you can see, that is protected with a plastic shield, here in yellow. Inside the cable, what we have is just a glass rod or a glass cable, and light travels through it. And that's how the information goes from one to the other computer. But then, why is this an issue with quantum computers? Well, the big problem is that the information in a qubit happens at a completely very different energy or frequency than the energy of the light traveling in the fiber. So you can think about them like two individuals speaking completely different languages. So we need to find a solution for this. There are many ways or many proposals on how to fix this, but in our lab, we choose a particular one. So we try to find a translator, something capable of speaking both languages. And for that, we use tiny little drums, like this one. This is a mock-up, a large mock-up of the real drums we use in the lab. For you to have an idea of the real dimensions of our drums, basically the diameter of the drums that we built, it's half the diameter of a hair, so 50 microns. So here you see the drum again, and what we see is that the drums is composed of two things. On the one hand, we have the frame, which would be here, this black part, and then the membrane, which is basically the part that produces the sound. And what is special about our drums is the material from the membrane. That's what we care the most about. Well, we choose a material called hexagonal boron nitride, HBN for us. But let me show you a close-up of what this material looks like. I have prepared this for you. This is, again, a circular membrane, larger, and we basically are zooming in into the drum. We zoom in so much that we are capable to see the atomic structure. So HBN is composed of two types of atoms. Here you can see in blue the boron atoms, and in yellow the nitrogen atoms. And what is special about this material is that its atomic structure it has the form of a hexagonal lattice. But where does the quantum part of, our drum or our system come into play? What is very interesting from this material, the reason why we choose it, is that sometimes the material is not perfect, but it comes out with defects. So basically, sometimes one atom is missing. These defects have some of these quantum properties. We use them as our quantum platform. And I promised you at the beginning that basically we will use the drums to communicate with the qubits, with the quantum systems. How does this happen? Well, this is our little hole. And now what you have to pay attention to is to the distance between the atoms. Let's imagine that the drum is moving. So it's basically going up and down. What you will observe is that the distance between the atom changes. And in this way, we also change the properties of these quantum systems. So we have fulfilled the first part of the translation. Our drum is capable of transforming the quantum system. But we need to go through the second part, which is basically how can we make the drum interact with the light, with the internet part of our system. So for that, you need to know that although it sounds a bit weird, when light is shining on us, it's pushing us. How does this happen? Well, light is composed of tiny little particles called photons. These photons are quantums of energy. This is a fancy word, but basically they carry momentum or they carry movement. So when these tiny little bits or photons impinge on me, they are pushing me. But then you can think about, well, when I go one day under the sun, I don't feel this force. Is it true what you're telling me? The thing is, yes, the problem is it's a very, very weak force. For you to have an idea, the magnitude of this force is similar to the weight of a grain of salt. So we don't see it when it comes from the sun. So we need to find ways in the lab to make this force stronger or makes its effects more observable. How do we do that? Well, the first thing is, instead of having a big drum, we decrease its size. And that's why we use these very tiny drums, which have the diameter of a hair. Why do we do so? Well, it's always easier to push an ant than an elephant because it weighs less. So we have our little drum. Here's the first thing we do. The second thing we do is, instead of using the light from the sun, which is not very intense, we use light from the lasers. So basically, we come with an optical fiber that we connect on the other end to a laser, and we send light to our membrane, like I'm showing you here. So now, because the laser is way more intense, so it's a stronger light source, the effects of the radiation pressure force are more observable. But we can even go a step farther. Now what we are going to do is we are going to add a second optical fiber that I'm going to place here. We are going to make them, or we are going to transform them into really good mirrors. So now these literally are like the mirrors from your bathroom, the fiber tips. So what is going to happen now? So now the photons are going to come and they're going to go once through the membrane. But because we have the other mirror, they're going to come back because they are reflected. And they're going to do so many, many times. So now one single photon interacts with the membrane up to 100,000 times. So this system composed of two mirrors is called an optical cavity. And for us, basically, it helps us to enhance as well the radiation pressure force. So now, what can we do with this force on our drum? Well, in this particular configuration, and if we do the experiment properly, we can use the force to basically drive the drum. So we can use it to give energy to the drum. That's equivalent to increase the amplitude of the motion. Remember that this was helpful for us to tune the properties of the quantum system. But we can also use the light to decrease the motion of the drum. And we can even go farther and use it to tune the frequency of the drum. So instead of being like this, change the tone like that. This was the main part of my PhD. Basically building an experimental platform similar to this one, capable of using the radiation pressure force to control and tune the mechanical properties of tiny drums. But then, what is next? So now we're starting a new collaboration with another group from MCQST. And it turns out that they are experts on the defects from these materials, so these quantum systems. So what we want to do in the near future is to use the drum to basically transfer the information through light, so use the light to communicate with the drum, and at the same time use the drum to basically interact with these quantum systems and control them. Now is a good moment to remember that the information in our internet travels through light, basically optical fibers. Of course, the experimental platform I've shown you here today is not going to be implemented in the next quantum computer, but it will, on the one hand, help us understanding the quantum properties of these new materials, but it will also help us understanding and figure out how to transfer the information between light and quantum system, taking a step closer towards the quantum internet. I hope that with this episode, you've learned a lot about quantum systems, light, and drums. Hasta la próxima.